Hello there, Veg here, and today I want to present my pre-designed hypersonic vehicle simulator built in Godot. Hypersonic vehicles are aircraft capable of surpassing Mach 5. That's 5 times the speed of sound, or approximately 6,200 km per hour. They are crucial for both the defense and the aerospace sectors, opening new possibilities for rapid air travel, strategic defense, and space exploration. Designing a hypersonic vehicle is incredibly complex. It involves multiple models and nonlinear equations caused by phenomena like gas ionization. So to streamline the feasibility analysis, we use one-dimensional flow in our preliminary CFD, especially to verify if the engine generates the necessary thrust. Here lies the problem. This tuning process requires a lot of trial and error. You end up performing dozens of calculations over and over again. To make this efficient, I decided to build the simulator focusing on clear, adjustable, and user-friendly UI. This helps prevent confusion and errors while tweaking the variables. I chose Godot for three main reasons: its simplicity, its clean interface, and its lightweight architecture, meaning it runs smoothly even on lower-end hardware. Of course, C# or C++ would be the superior choice for a final product due to how execution speed and access to external scientific libraries. However, for this stage of the project, GDScript is perfect for creating a rapid proof of concept. For the environment data, I relied on the 1976 US standard atmosphere. However, the original document is just page after page of raw tables. Instead of manually transcribing all that data, I leveraged Gemini to scan the document and convert the datasets directly into a clean CSV file. This setup allows the simulator to perform fast table lookups, automatically retrieving exact properties like density and pressure for any given flight altitude. For the hypersonic theory and governing equations, I referenced Modern Compressible Flow by G.D. Anderson. I structured the simulation as a sequential pipeline. For its physical phase, a specific node was created in the Godot scene tree. To orchestrate this, I built a separate manager node. Its job is to call the methods of each phase in the strictly correct order, ensuring that the output of one phase is correctly passed as the input for the next. Also, I heavily utilize Godot's export variables. This makes the system highly scalable and allows me to drag and drop dependencies directly in the spectre, simplifying variable access between steps. Now let's take a tour of the user interface. My goal was to move away from standard game menus and build something that feels like a legitimate laboratory dashboard. On the left sidebar, you have full control over the flight envelope, specifically altitude and initial Mach number. Up on the top right, you manage the thermodynamic constants such as fuel properties and the friction coefficient. Finally, on the bottom left, we have the geometry controls. Here you can fine-tune the ramp angles, component heights, and vehicle width using spin boxes. A key detail here: these inputs have a step value of 0.001. I implemented this height precision because highlight and funnel flows are extremely sensitive. A difference of just 1 meter can be the difference between a functional engine and a choked flow. Let's dive into the numbers. I ran a benchmark test comparing the simulator's output against the analytical solutions calculated manually. As you can see in this table, the shockwave solver is incredibly precise. Looking at ramp 1, the expected pressure was 840 pascals, and the simulator returned 839 pascals. That is a deviation of less than 0.1%. The Mach numbers throughout the compression ramps match almost perfectly, validating the oblique shock equations. Moving to highlight flow, the most complex part, the results are just as consistent. The calculated stagnation temperature in the combustor came out to 3,468 Kelvin against a theoretical expected value of 3,470 Kelvin. This confirms that the heat addition algorithm is handling the gas properties correctly. However, the simulation reveals a design challenge. If you look at the final performance block, our engine thrust is roughly 1,370 newtons, where the total drag is 2,360 newtons. In this specific configuration, the drag is higher than thrust. This proves the simulator is doing its job. It's not giving me a win screen. It's telling me that physically this specific engine geometry is not efficient enough for this altitude. That concludes the first part of the development. The project is available on GitHub if you want to inspect the GDScript implementation or the math behind it. I'm open to technical feedback or discussions about simulation engineering. Thank you for watching.